I have a problem. I need to find the average length from the centre of this square to the edge. First off, let's put some numbers in there, see what we can do. So we know for a square with side length 2 that the shortest distance, the centre to the edge here, is going to be 1. And the longest distance is going to be the square root of 2. In the second dimension, we have a line with start A and end point B. And this is our centre, C. So if we impose the problem to this line, we're trying to find the average length from C to one of the ends. Very obviously, these two lengths are going to be equal. So if we set them equal to x, we just have x plus x over 2, which is just equal to x. And you can prove that for any line. What do we do in the third dimension? Because there's an infinite number of lengths from the centre to the edge. So in the second dimension, we start with a square. And let's set the side length equal to 2. What if we just take a mean of the shortest length and the longest length from the centre, which would just be... What if we just take a mean of the shortest length and the longest length? The mean of 1 root 2, which is about 1.2. Well, that's not really taking into account every possible length, is it? What if we take the mean angle between the shortest length and the longest length? So this angle here is 45 degrees. If we're starting at an angle of 0 and we're ending with an angle of 45, then let's just try the middle angle, or 22.5. This length is going to be 1 over the cosine of 22.5. And interestingly enough, this just gives us the length of 1.08, which is quite a bit shorter than our first mean. Okay, well, let's take a few more samples, come up with an expression for how we might take more samples, and see if it converges on anything. So let's say we want to take 45 samples. How do we do that? Well, we know it's going to be a sum, and we know at the end we're going to have to divide by 45 the amount of samples we've taken. But what's our expression for these lines that we're getting? Well, as we know, the cosine is equal to the adjacent over the hypotenuse. Now, in this case, the adjacent will always be 1, but we're trying to work out the hypotenuse. Our expression is going to be 1 over the cosine of theta. So for this, we're going to set our theta equal to 0, and we're going to end at theta equals 45. 1 over cos theta. Now that's quite close to our original mean of 1 and root 2. But we need to take more samples. So what if we increase this? Well, this is the number of samples we're taking. Let's say that's 200. Well, we're not measuring our theta between 0 and 200 degrees, so we need to express this as a fraction of 45. Or we need to say 45 theta divided by 200, because as theta approaches 200, we will just be measuring the cosine of 45, which is what we want, but at smaller intervals. Okay, you can expect that this will give us a different result. It's not majorly different. The value we get for this when we compute it is about 0.01 lower than our mean for 1 and root 2. But it's still not enough samples. What we really want to do is take an infinite amount of samples between here and here and take a mean of them all. Well, how do we do that? We have to take a limit. Well, we want our value to go to infinity. As Rx approaches infinity, we take the sum as we did before. 0. And now our infinite amount of samples is going to be x. And then we've got to divide it all by the number of samples to get a mean. Now this will just be x. If we plug infinity into this limit, it's indeterminate. This is where integration comes in, because this is similar to the Riemann expression of an integral, but it turns out it's a lot simpler than that. What we're really doing is integrating between theta being equal to 0 and theta being equal to 45 of 1 over the cosine. That'll give us an infinite amount of samples. Now we just have to divide this by 45 because that's the amount of angles we're integrating between, kind of. So what does this value give us? It seems to be converging on something, about 1.12. Well, what is this value? I don't actually know, but I can tell you what it's close to. Say we take our square with side length 2 and an area of 4, and we take a circle which also has the same area. What's the radius of the circle? Well, we know that 4 equals pi r squared for the circle, because that's an expression for the area. So our r is just going to be the square root of 4 divided by pi. And lo and behold, what does this value equal? But 1.128, which is incredibly close. They're not exactly the same, but it's incredibly close to our value before for the average distance or mean distance from the centre of the square to the edge. Say we take our square and we inscribe and conscribe circles. Well, we know that the radius of the larger circle is the square root of 2, and the radius of the inner circle is going to be equal to 1. But what we found is a circle with a radius equal to the average length from the centre of the square to the edge, and an area also very similar to the square. What do we do from here? it's time to generalise. For any supposedly regular shape polygon, we can express the longest length to the centre and the shortest length to the centre in one triangle. This one. And it will always be right angled. So let's just draw a triangle and add in some variables. Now the shortest length is the perpendicular bisector of our edge. So we know that this top length is going to be the length of our side divided by 2. So what's this and what's this and well, that's 90. So how do we express this angle in terms of n, how many sides we have? We know that for an n-sided shape, the angle for one edge is going to be 360 divided by n. But because we're halving it, we have to use 360 divided by 2n, or 180 over n. Now that means that this side is going to be 90 minus 180 over n. What's our x going to be? The numerator in our integral. From the sine rule, we know this, and it follows that x can be expressed this way. I think we're ready to express our final integral. We're always going to be integrating between 0 and our theta, in any case. Now, our theta is 180 over n, and we know that in previous examples we had our hypotenuse is equal to our adjacent over our cosine, and now our adjacent is expressed in theta as well, with a variable L for the length of our side, which doesn't really matter. Now what will we be taking the cosine of? Because it's not theta. Theta is what we've used as our limit and to express other properties of the shape. We really just need a variable. Let's say phi. And since we'll be using phi as our variable, we just say d phi at the end. And that's our final expression for the average length from the centre to the edge, and by average I mean mean, of any polygon. Now you'll see the graph on screen now, and it's quite confusing. Obviously, after a two-sided shape we have the triangle and the square. The black line is the radius of a circle with area the same as our polygon. For those interested in a final expression, we can do this. Now what this equation shows is that this, the radius of a circle with the same area as the polygon in question, is very close to the average length from the centre of the polygon to the edge. In fact, it's so close after a square that it's basically indistinguishable. Now, interestingly, what we can do is rearrange this to get an expression for pi. This is kind of circular. I mean, yes, it does give you an approximation for pi, but you're putting pi into the theta, you're using trig functions. It's not really an approximation at this point, it's just a weird expression. Now you can see the graph on the screen, and I've put it in a logarithmic scale so that you can see when it starts to break down. When the polygon has so many sides it's basically a circle, this function just breaks and it doesn't approximate pi anymore. And if you zoom in, you'll see little lines. It sometimes happens with trig functions. Anyway, I just thought this was cool.